glad to be invited to this the workshop, and I'm sorry I couldn't be there. Our travel ban just got lifted, so yeah, it would have been wonderful to get there. It's a very early morning for us here. It's 8 a.m. But I have been listening to the talk just before this one, and I think it was a nice segue to my talk, because you will see some of the structures you have seen in the previous talk, in my talk as well, only in a much, much smaller scale, because this is going to be a theory talk and mostly for the nanoscale structures. But it would be also on silicon nanostructures. So hopefully there will be some synergy between the two talks you can see. So to get started, what we are doing in my group is we are trying to control phonons with nanostructuring approaches for multiple different applications. This is kind of a brief snapshot of different projects that is going on in my group. The first one in the left, can you see my my pointer? Can anyone please comment? Okay, okay, perfect. Yeah, I can see the audience a little bit. Thank you for showing me that view. It feels like I'm still there. Yeah, this is the first part, first project is the one I will be mainly focusing on today, which is the how, when you go to the nanostructures, nanostructure geometries, how the confinement, the surfaces, how does it affect the phonons, and how can we actually kind of determine the nature of the phonons, their propagation, and so on. That's going to be the main highlight of today's talk. Other than that, we have also been focusing on a lot on kind of heterostructures, semiconductor heterostructures, silicon and germanium heterostructures, and especially focusing on how the interfaces, the strain at the interfaces, the defects, how does it change the phonon electron transport in there, and as well as the electron-phonon coupling through that. This was mainly for the thermoelectric applications, because this is kind of the superlattice structures you are mostly familiar with. The other three topics we are also investigating right now is the bottom left. This is kind of the data-driven models. I will bring up some of the concepts from here to this talk as well. The idea is that when we are doing like atomistic modeling, we are kind of limited to very, very small system sizes. But on the other hand, you have the fabricated nanostructures, which are kind of billions of atoms. So there is always this huge gap that how can you predict the properties of these nanostructures that could be fabricated in experiment. So we are trying to use machine learning techniques to establish a gap bridge between these between kind of the atomistic models as to the fabricated nanostructures. How can we use machine learning models effectively? That's the highlight of this project. I have other two projects going on, which is kind of using phononic concepts for neuromorphic architectures. I won't be able to get into the details here today. As well as another one for quantum applications, where how qubits relax in when it couples to phonons of the structure. So these are, so for all these applications, kind of the basic philosophy is how can we control phonons so that you can improve all these different applications. So as I mentioned that I will focus on the first two projects on the left side. To the top left, that's the first topic. And this is where I started collaborating with one of the organizers, Sebas Repers, and this was done like 2015, a long time back when I was in Germany as a postdoc. And this was one of our kind of beautiful project. What we tried to do is we tried to understand, so this project was also geared towards thermoelectric applications. And we wanted to understand how can we use ultra thin silicon membranes for thermoelectric applications? That means, can we reduce the thermal conductivity by making the membranes thinner and thinner? So to the left, this is kind of courtesy the VTT Finland. They fabricated this amazing like 9 nanometer thick membranes in lab, and our job as a theorist group was to model the thermal conductivity of these membranes that got fabricated on these structures. So to begin, we started doing atomistic modeling, which we can see that these are the models. We use periodic boundary conditions to kind of mimic the infinite directions in plane direction. And as you know, like when you cleave the 001 surface of silicon, they get dimerized on top and bottom. So that's what is shown. So this is like 5 nanometer, but we tried like between 1 nanometer and 20 nanometer, different kind of thicknesses. And this was published in 2015 that, so what we did is our main aim was to predict thermal conductivity of these ultra-thin membranes. And before even we started, there was a lot of reference data because this silicon is not a new material and there are a lot of like SOI and all this kind of data was available. So this was kind of a patch of the reference data. All experimentally measured data were available for us. And it was known by that time that as you reduce the thickness, you do reduce the thermal conductivity slowly and slowly. So we wanted to kind of just match that with the atomistic calculations. And what we saw is that first, if we have this like pristine surface, like I showed in my last slide with the dimers on top, we do see a reduction of the thermal conductivity, but not as much as shown by this reference data. So then we started thinking a little bit more, and then we wondered that maybe our system, like atomistically clean, pristine surface wasn't that great. So why don't we include some of the roughness? So by roughness, the way we did it is we assume like there are some pillars, and then when you anneal them, it became something like a dome on surface with kind of periodic roughness. That's how we simulate, model the systems. And immediately we saw that there is like a reduction in the thermal conductivity. This is the blue points because of the roughness. But it was still not matching the reference data. So then we discussing with Sebas and others, we realized that when you expose silicon membranes to atmospheric conditions, you have all this oxidation forming on top of that. So we must include that into our picture as well. And as soon as we did that, this is kind of the oxidized membranes with the layers on top. Immediately we saw that there is a huge reduction of the thermal conductivity as well. And then we tried like both oxidation and roughness, but we saw there is not much difference between the two sides. And then Sebas did this amazing experiment that with the 2-laser Raman thermometry. That so here you can see that the open rhombus is the experimental data which was measured by Sebas and the group. It was matching perfectly with our oxidation, the model we predicted. And then these green ones are the ones that is the etched out oxide layers, native oxide layers, and immediately the thermal conductivity increased. But then they do kind of, I think 6-hour oxidation, kind of a controlled oxidation, and it became like in between. So what this kind of experiment in theory story told us at that the surface disorder and roughness is the key, and it influences the phonon transport to a great extent, almost like determining 40-fold reduction we observed in thermal conductivity of 4 nanometer membrane. So, so this became kind of the starting point of this story, which I want to share with you today. So then the way we did it, and I'm sure you are quite familiar with this topic, is at that time we used the classical molecular dynamics, and we used the Green-Kubo formula to find out the heat current autocorrelation to find the thermal conductivity. Of course, there's a lot of issues which you may have heard in another talk before, that one has to be kind of simulate long enough and for large enough systems, and there's convergence issues, and all this we had to take care of that. And then there's like equilibration, modeling of surfaces, thermostats, and all these things. We did that, and we used LAMMPS and DL polycode, and used empirical potentials, which was already proposed before. And although TERSA has lots of shortcomings, but it is now established that it can reproduce results for nanostructures pretty well, especially when you compare the thermal conductivity between bulk system as well as and the nanostructures. The ratio it can predict pretty well. The exact value of thermal conductivity, it still has some limitations for that. So we did that. And then we were more curious to find out like what is really happening. Like, sure, we saw the thermal conductivity reduction using because of the native oxide layer, but why, what is happening to the phonons? So then we did some non-equilibrium molecular dynamics simulations for different length of the system. And we use that to kind of predict the thermal conductivity accumulation for a certain sample of certain length. And what we saw is that as we oxidize, as the native oxide layer forms on top of the silicon membranes, we get more and more contributions from low mean free path phonons, as if like the longer mean free path phonons, the transport of those are getting suppressed. So that's what I tried to show. This is kind of the membrane, and as you go to this rough and oxidized and oxidized plus rough, you get almost like 15%. By like this point, you are already 80% of the thermal conductivity already got accumulated. So that tells us that there must be something happening to the phonons, and something must be reduced because of the surface native oxide, which is kind of producing this thermal conductivity reduction. We also did, try to find out from other different methods. The idea is the same, to identify what kind of scattering is present in the system. This is also from the non-equilibrium molecular dynamics. What we did is we calculated the kind of the heat current autocorrelation function and the Fourier transform of that. And that gives us the transmission function for a particular frequency and particular length. And we kind of did it for multiple different lengths, found the ratio of that to find out the mean free path. So the bottom, so what this plot is telling us is that if you have the pristine silicon membrane, the mean free path is falling off as 1 over omega squared. On the other hand, if you have like embedded germanium within the membrane, so this is kind of the embedded scattering, which mostly we have seen people using to disrupt the transport of phonons, then you have 1 over omega to the 4th. That's kind of the line. Now, if you have the silicon with the silica on top, the silicon and the native oxide layer, it's like so here the difference between the two is here the low frequency phonons are not interrupted as much, but the high frequency phonons are getting interrupted. But here on the other hand, the low frequency phonons are more interrupted, and there is some effect on the high frequency ones too. And then if you combine, you get like the best of both worlds to reduce the thermal conductivity. So this is kind of telling us that this scattering or whatever it is happening, it is different than those embedded scatterers, the effect of those on the thermal conductivity. So now definitely we want to understand that what is happening from the phonon side, that we saw all these kind of effects influencing the thermal conductivity. So now we want to understand that is it only surface scattering or something happening inherently for the phonon modes? Is the dispersion relation changed, or the group velocities change, or all of the above? What is really happening? So that is kind of where we spend time investigating, following up from this story. So to do that, of course, we have to go towards the kind of the kinetic theory of carrier transport, which you also heard probably today earlier from other talks, that once you go to this kind of Pearls-Boltzmann equation in this PB, the phonon gas model, we are still assuming that it is following phonon gas model, although I will show that there could be some doubts about whether the phonon gas model is actually valid for this system. But to begin with, we are using this framework, and within this framework, as we know that the thermal conductivity can be expressed as the group velocity squared times the relaxation time. And the way we calculate the group velocity is we diagonalize the dynamical matrix for the full supercell. We have using the nanostructures on top, the surface nanostructures. And from there, we can calculate the dispersion relations. We can calculate the eigenfrequencies and eigenvectors. From the eigenfrequencies, we can calculate the group velocity, as well as using anharmonic lattice dynamics, we can calculate the relaxation time. So that is kind of the general framework which we have used to get the results from the following slides. So again, before doing that, we first started because the oxide was so kind of intriguing to us. This was not lattice dynamics, this is from the molecular dynamics. Here, what we do is essentially take kind of the Fourier transform of the trajectory to get the dynamic structure factor. So this is an oxide kind of a system that we have the membrane here, and on top of it, this is kind of the native oxide. What we saw is that if you do the same thing for pristine, you get kind of the clean modes over here. This is a little bit hard. First of all, this is very expensive. There's like a lot of computation power needs to be going there. And, but still, once you do that, you say like kind of clean lines for the membranes, but once you get to the one with native oxide, we saw a lot of kind of this, the lines here, which are parallel. So it's a little bit hard to identify these, but you can see like these are kind of the dispersionless modes are appearing right over here. And then we tried to also kind of identify that where is this happening? Is it in the middle? So the 3 region is right in the middle. So you can see in the middle, we have very, very clean picture. But as you go towards the surface, you see this appearance of this dispersionless mode. So that means like this is where the idea comes from, that might be the local properties are changing because of the surfaces. So that's kind of the idea we are going in. So to get to the kind of further details, of course, we are going to the lattice dynamics. And here we are looking at more kind of periodic samples, much more well-behaved. It is harder to do with the oxide because of the amorphous layer. So we are going towards more ordered structures. So first of all, this is kind of the basic membrane with the dimers. I think this was kind of 1 nanometer or something like that. So because of the presence of the dimer, your supercell or unit cell, whatever you call it, it becomes huge because you have to include both the top and the bottom. So you kind of take a slice of that as your supercell with the vacuum on top. So it could, the number of atoms you have to analyze grows pretty fast as you make the membrane thicker and thicker. So to the left, you have the bulk silicon. Everybody probably have seen that. You have like the LA modes, TA modes, and LO and TO. And then when you go to the membrane side, there's many more modes because there are many more atoms we have now in the system, but you can see like it's kind of the much more softer, and then there's this flexural breathing mode. These are the new modes that appear in membrane. So what happens is when you go from bulk to membrane, that you had the LA mode and TA mode, but for bulk, you had 2 TA modes. Now, when you go to the membrane, one of the TA modes becomes this outer plane flexural ZA mode. So that's kind of these modes appearing there. And as you'll see that once we put the nanostructures on top, these are the modes that get quite a bit affected. But because of kind of the flattening of these bands, that's where you can already see that the group velocities are going to be reduced, and this kind of leading to the thermal conductivity reduction. But as I said, that these modes are not same as the bulk modes. These are kind of different because of the boundary conditions and so on. So we tried to also, and that same story kind of tried to match, and what we saw is this ZA modes are getting affected with the decreasing thickness. So from red to green, it's becoming much more flatter as you make it thick. So it's kind of expected because you will be easily bending these membranes once you are making it thinner and thinner. So that was kind of the membrane. Now the next step was kind of introducing some of the structures on top. The first one, we used the pillars, and this is also one of my colleagues did a lot of work on these kind of structures, and it is a lot of group kind of also noticed that because of these pillars, there's a lot of reduction that happens in the thermal conductivity. And once you do this kind of lattice dynamics, what you see is that if you have these little nanopillars, these are just 1 nanometer pillars. I think this membrane was 3 nanometers, so 3 to 1. So you can see like the surface is affecting a lot. So what you see is this kind of these flat modes appearing once you have the structures on top. And as a result, if you calculate the group velocity, which is just the derivative of this frequency with respect to Q, then because of these flat modes, they have almost zero group velocities, very, very reduced group velocities. And that is happening very early on, like 0.6 terahertz, where the heat conduction happens mostly. So because of this low group velocities, definitely you can see that the thermal conductivity would be reduced. And why that is happening, the explanation was kind of provided by my colleague first, that once you have this membrane, so you have like the propagating modes, and then you have the surfaces which acts as a resonator. So those resonances kind of that is locked in the surface structures, they can move up and down the structures, and that's what and then they can hybridize the in-plane modes. So you have like a different kind of hybridized modes that is going on in the membrane. You can either call them mode coupling between the membrane modes and the resonator modes on top. Or you can, this is now known as resonance hybridization. But because of these, the membranes become something like a metamaterial, and the properties of these phonons are different from the materials that was before. So that is kind of the idea that because of these, you have the flat bands, where the coupling is happening, and as a result, you have quite reduced group velocities. So we try to kind of understand that where are these modes, what is happening there. So if you go kind of so we only calculated this at the gamma point, and we saw that this is mainly locked there. So here, what you see is that the black lines are just the membrane modes, and the red is what is happening when you have surface structures on top. So the black line, like 0.83, that was that membrane mode, the black one right over there. And once you have this resonance hybridization, what happens is that they are mostly confined to the surface structures, and there's like a silence, the phonon silence, so there is no displacement happening in the middle of the membrane. So that means there is kind of no propagation is happening. As a result, no heat carrying is happening. So there, like all these different modes, there's a lot of different kind of modes, but I highlighted only a couple to show you that the idea that hybridized phonons are inducing some localization of the phonons, which was previously extended all over the membrane bulk. So then the question is it happening, for all different kind of structures? And this is where I said that there would be some similarity in the structures which the previous speaker showed. But again, this is much more smaller scale. So we also considered the nano fins on kind of the one on top of it. And again, this is the difference between these two in our case, is that this particular structure with the pillars is symmetric if you go like look at X and Y direction. But here, if you go along the fin versus across the fin, the surface structures becomes different, the environment becomes different. And that has a lot of impact on the thermal conductivity, as I will show later. So the first thing is we calculated the thermal conductivity, of course, and here is the plain membrane with the surface structures, with just the pillar on top, we have seen reduction, and it's kind of the 20 nanometer with 1 nanometer, you can see kind of a trend that the thermal conductivity, in general, it's always less than the membrane, but there is kind of more of a reduction as you go thinner and thinner. Here for the fins, what we saw is kind of interesting is that there's, because of the two different environment, that if you can go across the fin versus along the fin, you see different kind of reductions. In fact, if you, it might be hard to see just from the plot, but when you kind of took the ratio of along the fin versus across the fin, it was almost a factor of 2 difference. So what we see, like some kind of anisotropic in-plane thermal conductivity in isotropic silicon membranes, which is just induced by the surface nanostructures, which is kind of quite interesting for us to see. Because anisotropic thermal conductivity, as you have seen, that there are many reports for different kind of materials which has different bonding environments. That's where you see this anisotropic one. But here you have the same bonding environment in the in-plane membranes. But because of the surface structures, now we see this anisotropic transport behavior. So again, we went back to understand what is happening from the phonon side. And this is the panel I showed you before just with the membranes. Now I added the fins. And what we saw is that if you go across the fin, like perpendicular to the fin direction, you see similar kind of flat, they are not as flat, but quite flat. The dispersion, less dispersion or dispersion less modes over here with the almost 0 group velocities and so on. But on the other hand, if you go along the fin, you see this kind of a guide-like modes, which doesn't have 0 group velocity. It actually maintains quite a bit of group velocity here. It's somewhat reduced from the membranes, but it still has that. So you can see, like, from just looking at the dispersion and group velocity point of view, we can see that there are some anisotropy happening at the phonon mode level. Now, so here, this is kind of the idea that where these modes, and you can see like these are sort of the guide modes happening in the membrane. So previously the membrane were only localized right on top, but here it's kind of extended through this entire fin system. So we tried to kind of quantify how much it is localized. So we calculate the participation ratio, which you can calculate from the eigenvectors. And so the idea of the participation ratio is that if you have extended mode, your participation ratio is almost 1, that most of the atoms are participating in a certain mode. But if you have a localized mode, the participation ratio goes down. So that's what you see kind of here. It's on an average, the bulk and the membrane is on top, high participation ratio. But as you have like the surface nanostructures, your participation ratio goes down, which is indicating that these are more localized as you have the surface structures, which is the pictures, the displacement diagrams also show us the same thing, that it is more localized there. We also calculate the kind of the relaxation time. These are very, very heavy calculations because these are like 5,000 atoms or so on. And we saw a little bit of kind of anisotropy here, there too, that what is interesting, like the low frequency relaxation time is almost becomes flat over here. Although we don't have as much sampling because the sample size is pretty less, that here in along the kind of the perpendicular direction, you have flattened relaxation time, but here you do not see that flatness. So we can see like something is happening anisotropic from this kind of viewpoint as well. So this idea that the localized modes, are they really the phonon modes, which we are known like they have to be extended all over? So that's when we started thinking that this might not be behaving truly like a phonon gas model, that there might be some kind of glass-like transport is happening because of the localization of these modes, because we saw like many modes are localized compared to the extended mode, which we see in the membrane. So we try to use this quasi-harmonic ring-Cobo theory, which was just proposed in 2019. And there are many other theories are also, there are two theories which also deals with this kind of both crystal-like and glass-like transport. And they extended this Allen-Feldman model. So Allen-Feldman model was about just for the glasses, the quasi-harmonic glasses, that you have like kind of the simple harmonic states, the disordered states, and they can kind of share heat between the modes, but they are not they're still localized, but they can exchange the heat from one to another. And you go to a like heat flux operator, and from there you can define something like a heat diffusivity of those modes. And then using the diffusivity, you can calculate the thermal conductivity. So diffusivity kind of shows you that how much one mode can give away the heat to the other. Here on the top panel, I have the the one with the pillars, and here one with the fins. So here you can see like this zone, we have low diffusivity, the modes with low diffusivity, which is kind of signaling this glass-like transport. So, and what is even more interesting is if you go to the fin side is here you have clearly like separation of the two directions. The green one is across the fin, which is the low diffusivity modes, which we are terming this as a glass-like modes, versus the orange one, which is the high diffusivity crystal-like mode. So this is, both of them are happening at the same time. But if you go towards like different directions, you see different kind of behavior of these modes. And as a result, you come back to this anisotropic thermal conductivity as well from this picture. So all these different models are telling us the similar behavior. That's why we try to use them for different purposes. Do you know how much time I have?
10 minutes.
Okay, thanks. So these fins were quite interesting for us. So we tried like close-spaced versus wide-spaced nanofins, and again we see kind of similar kind of anisotropic behavior for both the cases. And you can see like this is across the fin, we have the flat panels, and then we have the guide-like modes for close-space fins and wide space, and then the similar kind of behavior over there. So now we wanted to kind of quantify what is happening. And the idea is that how can you use the surface nanostructures to really control the different phonon modes, their propagation, their localization, and so on. So if you go by like these kind of where these are, so we wanted to kind of label them by different localization. So if this is localized, how much localization is this? This is guide-like, what does that mean? So that is the idea. So the localization, this kind of this prescription was proposed by Phil Allen itself for glasses, that in glasses you have localized modes. That means if you have a chosen center of the localization, that is R0, if you go from R0 to R, the mode shape, the kind of the projection of the eigenvector would fall off with some decay constant. So that is how we are terming that as a localization length. So how quickly it decays, that means the mode is more localized and so on. So here I've shown some of the modes here. So you can see in the fin region, it is still there. So our center we have chosen as the center of the fin. In the fin region, we still have the mode, but as soon as it comes out of the fin, it immediately decays down. And it is apparent in both of the close-spaced and wide-spaced the nanofin configurations. And of course, there are different kind of plots because the wide fin is much more, the supercell is larger. That's why you go farther to kind of decay. So that gives us a good idea. But what about the along the fin? Because that's the anisotropic behavior we've seen. So because to capture both of them, we said, what about thinking about a complex propagation constant instead of like the real decay? We are now thinking about both the decay plus an imaginary one, which could give us the propagation there. So there's a lot of modes, and we analyzed, and there are a lot of values. I'm showing only a couple. Kind of the bottom line is that For the closed spaced, we see many, many more localized modes. For the wide one, we see less, but their localization length is of the order of 10 or so. So which is kind of right in between the fins. That's where they kind of die there. So there's a lot of things. Then what we try to see is like the displacement profiles for different kind of ones. So here, this is one of the localized modes, which has like a wave-like form along the fin, which is the propagation kind of, we can say like it's behaving like a guide. So there are many more pictures I could show you. We are really investing. Some kind of, these kind of pictures are also very interesting to see that how the modes are more localized and where they're spread and so on. But let me move on, because what is happening is because of this localization, when we did kind of the non-equilibrium molecular dynamics, what we see is that right where your fin ends, the membrane starts, that's when we see some kind of a jump. This is the similar Kapitsa-like jump we have seen for when you have two different dissimilar materials, the thermal boundary resistance or conductance we heard in the last talk as well. But here it is happening in the same material because of the surface structure. So what we kind of now believe is that because of the localization, your modes are being localized within the membranes, and that's where there is like a jump that is forming. But of course, it's a very, very tiny jump of the order of 1 Kelvin or so. So it's quite fine. And yeah, so because of that, we see this kind of, and we see it both in closed spaced and wide spaced one. The wide spaced one has a more clear jump than the closed one. And of course, we kind of rediscovered the anisotropic one. So the anisotropic one, now we have established is like in 3 different models. So since we are theory group, we try to do like multiple different models to really establish the phenomena. So we believe that this is really happening over there. This is the other interesting thing we have seen is this is coming from the membrane. So I have shown you the mode displacement patterns, and now we can also see some kind of strain in the monolayers when we do the molecular dynamics. So the interesting thing is to understand is how does those mode shifts contribute for this kind of different non-uniform thermal strain environment in the system. So we are still figuring that out, that what are the modes that is contributing to this strain profile, because there is some very interesting profile happening right over here. And these are only equilibrium molecular dynamics patterns, that there is like kind of hot patch with more close spaced versus farther separated monolayers because of this displacements happening, which is linked to the phonons, but that connection is kind of missing to us. So I probably have only a couple of minutes left, but as you can see, like there are a lot of data available here, a lot of mode shapes, and as a result, we have non-uniform thermal environment. That is where we started thinking about that. How about data-driven modeling? And in my group, we have been using data-driven framework for electronic property prediction. And as I mentioned at the beginning of this talk, the idea was that how can we have a bridge between really tiny DFT, density functional theory models, to fabricated structures. For example, here, this is kind of the superlattice structure at the to the right side. I'm showing this is like a 12 nanometer large structure, which is of course not possible to do with density functional theory. So what we did is we broke this into chunks of little like environments. For example, you have the bulk of the silicon, bulk of the interface between the two, as well as the alloy region here. And we broke this up in 16 atom pieces, and that's our training data. We calculated kind of the energy states, then fed that to the machine learning model. And you asked it to predict electronic states, the bands for larger structures, and then use Boltzmann transport equation to calculate the Seebeck coefficient from there. So this is quite successful, and we were matching the experimental measurements before from here. And the idea was that how can you predict the transport properties from the local structural order? So that's kind of the similarity we wanted to kind of borrow from this study to the phonon study over there. So this is only a beginning of this phonon study, so we haven't published anything, but what we just started doing is looking at these kind of configurations, like for example, this is a superlattice and this is the fin. So these are our like training structure, that looking at this training structure, can we predict some more complex structures where they are like more alloy with the fin and so on. So this is kind of just, we're trying to play with it. So our training data is this trajectories and kinetic energy and so on, which is geared toward the temperature. And what we focused mainly is what kind of features we need to capture from this data in order to predict the property. So property means the temperature, for example, here, because the temperature showed us all these jumps and non-uniform behavior. That's what we wanted to predict. So we used multiple different features, for example, these are all done with non-equilibrium molecular dynamics, where you have a hot side and a cold side, and how far that is, where is the atom with respect to the hot side and cold side. That is one of our features. And then other one is this local features, which is very crucial. We realized that if you want to predict the jump at this, and what we did is we calculated like this Voronoi tessellations, and from there we looked at the network of the atoms and how much each atom occupy within the structures. That's kind of a very qualitative way of doing it, but we have all this information available in the paper we just published. So this is a similar order parameter feature we have used for the electronic property, and now we are using the phonons. And what it does is, this is quite interesting, is it uniquely identifies the environment the atom is in. And that's what we believe is one of the key to predict the local temperature jumps and non-uniformity in the temperatures. So here are a couple of examples. Of course, machine learning produces tons of images that you have to make sense of. What we have seen is that if you use all these different features, like global means where are there hot and cold bath are, as well as the local, what is the unique environment the atom is sitting in, you actually can predict. So this is like a silicon with silicon germanium alloy interface systems. It can predict the profiles rather well. There is some kind of, there's a lot of things I can comment about, like which model does better, the random forest versus neural network and so on. But this is the part we are figuring out, that why is one model behaving better than the other. Then we also try to kind of see that these structures are 40,000, 50,000 atoms. So it is quite difficult from the computational point of view to understand the environment of each different atoms, and which we now think is not necessary because we are trying to bin them in kind of a cluster. And so that's something we are trying to do, this if we can also do it. Then we tried like this global features versus a local feature. So what is interesting is that global feature cannot do the right at the interface jump very well, but local features are worse in doing that, but just at the interface, it is doing pretty well. So you need to have multiple different features to do that. I think that's kind of where I'm going to wrap up, because this is an ongoing study, and what we are trying to do next is first trying to see if this MD kind of properties are being reproduced by these machine learning models. The next would be like, how can we have a bridge between what we observe in the MD versus what we observe in the phonon modes using lattice dynamics. So that's kind of where we are going at. So I think what I have tried to show you here is that the surface structures are directly influencing the phonon transport here, and especially the local properties are so different. So what we believe is that this kind of surface nanoscale engineering can guide the heat in a very interesting way. And this is kind of gives us a lot of tunability to control the local and global thermal properties of this. For example, the anisotropic thermal conductivity, I showed you that we have multiple different models kind of validating that is True. Unfortunately, we do not have any experimental evidence for that yet, but hopefully this is inspiring some of the experimental friends here to look at that as well. But what is from the fundamental side, it's quite interesting is that we see both different kinds of phonon transport happening. And we think that this is because of this mode coupling between the surface structures and the membranes, which gives us a lot of power to control the properties of phonon modes there. And that's where we are bringing in the machine learning models, that how can it use the surface structures to control the individual mode propagations, hopefully in future. I would like to acknowledge my group, Morgan Henderson, the PhD student who did most of the work. You have shown, you have seen Artem Pimachev, the postdoc, who is the machine learning person. And then the other students are also supporting this idea. And we gratefully acknowledge the funding sources which made this work possible. So with that, thank you for your attention.